Dear student, in this video, we discuss about the flow parallel to a semi-infinite plate in the boundary layer theory. Let us consider a thin infinite plate submerged in a steady incompressible plane parallel plate whose undisturbed velocity is small u. The fluid has low velocity and the plate is at rest in such a way that it's the plane considered with the direction of capital U. Since the x-axis is laying along the plate parallel to the v and y-axis normal to the plate, so the velocity small u of the potential flow is considered in this case, so that capital U is equal to constant and d is equal to 0, and hence dp by dx is equal to 0. So the plate is placed in uniform fluid, then the motion is steady, so therefore delta u by delta t is equal to delta v by delta t is equal to 0. So the frontal boundary layer of equation in this case under consideration are u del u by del x plus v del u by del y is equal to nu into del square by del y square, and del u by del x plus del v by del y is equal to 0. This is our equation number 2. So the boundary conditions to be satisfied by the u and v are u and v is equal to 0 when y is equal to 0, and u is equal to capital U when y tends to infinite. This is our equation number 3. So the integration of equation 1 and 2 can be simplified by the reducing the number of unknown with the help of stream function u is equal to del psi by del y and v is equal to minus del psi by del x. This is our equation number 4. So the equation 2 is satisfied on the mathematically equation 4. Now we take the now dimensionless parameter neta is equal to y upon this, so that neta is equal to under root of this. So neta is equal to y into x ki power minus 2 into under root of capital U upon nu. Let the velocity profile be small u upon capital U equal to f neta. Then is equation 4, 5 and 6. The stream function is given by psi is equal to integral u dy, psi is equal to integral u f neta dy, and psi is equal to integral u f neta dy upon d neta into d neta, and neta is equal to y upon under root of u upon u into x. So under root of nu into x upon u into neta is equal to y, also under root nu into x upon u is equal to dy by d neta. So psi is equal to under root capital U into nu into x into integral f and neta. So phi is equal so psi is equal to under root capital U into v into nu and f neta, where f neta is equal to integral f neta. Using this equation 4, 5 and 7, then we get u is equal to u f dash neta. This is our equation number 8. Now similarly we get v is equal to minus delta psi by delta x is equal to minus f neta delta by delta x upon root u into neta into under root x plus under root nu into u into x upon delta by delta x of f neta. So v is equal to minus f neta into 1 by 2 under root u into neta x ki power minus 1 by 2 plus under root u v into x upon delta by delta neta of f neta delta neta by delta x. So v is equal to minus 1 by 2 to f neta upon under root x into under root vx plus under root v into x f dash neta y into neta. Solving this equation, then we get v is equal to 1 by 2 under root of u neta upon x into f neta minus f neta. This is our equation number 9. Using this equation, then we get del u by del x is equal to minus u upon 2 neta f double dash neta del u by del y is equal to f double dash neta into under root u upon u into x. This is our equation number 11. And del square u by del y square is equal to f triple dash neta into capital U upon vx. This is our equation number 12. Substitute equation 8 to 12 in the equation 1. Then we get twice f triple dash neta plus f and f double dash neta is equal to 0. F triple dash neta means differentiation of beta with 3 times, and f double dash neta means differentiation with respect to 2 times. And the boundary conditions are when y is equal to 0, u and v is equal to 0, and when y tends to infinite, u is equal to capital U. So the boundary condition become when y is equal to 0 and neta is equal to 0. This means u is equal to 0, so f dash neta is equal to 0, so f dash neta is equal to 0. When v is equal to 0, this implies 1 by 2 under root u into nu upon x into 0 into f dash neta minus f neta is equal to 0, so f neta is equal to 0. This means y is equal to infinite. When neta tends to infinite, this is equal to small u is equal to capital U. This implies capital U is equal to capital into f dash neta, so f dash neta is equal to 1. So the boundary condition become when neta is equal to 0, f and f dash is equal to 0. When neta tends to infinite, f dash is equal to 1. So equation 13 is a third order non-linear differential equation. So the boundary condition completely, but the general solution of theta not be possible. So the closed form, as Blasius obtained the solution in the form of power series expansion about neta is equal to 0. By this method we find that f neta is equal to summation n is equal to 0 to infinite alpha n plus 1 into n into eta 3n plus 2. So where a0 is equal to 1 by 2, a1 is equal to minus 1 by 3, a2 is equal to this, and a3 is equal to this. Verify is not the boundary condition of the infinity. So in this all equations we can get the result.